So good morning everyone and welcome to this lecture. We were dealing with law of conservation of angular momentum. Do we remember this question? Do we remember this question that we discussed in the last class? Where the momentum was conserved, where it was not conserved. Do we remember this?
Yes, sir.
What we remember? That the linear momentum was not conserved because of the hinge. The angular momentum was also not conserved, but about the point O, the hinge point, the angular momentum was conserved. Yes or no?
Yes, sir.
We come to this type of questions. And this type of questions are known as questions of eccentric collision. Eh? Eccentric collision? What is that? What is eccentric collision? Yes. Again, we might have become Gajnis.
No.
Remember what is eccentric collision? Tell me what is eccentric collision. Sir?
No, sir. No idea.
No, sir, no idea. Get idea. That is the problem with us, that we forget things. We forget things, and that's not a good quality to have. Not a good quality to have at this point in time, and that is why I keep proof of everything that we have done in the class. I can tell you the lecture number as well. This is lecture number. Lecture number 1 in collisions. That we did this. When we started collision, the first thing I told you about collision. The first thing I told you about collision. Did you care to write it down? No one cared. I did write it down. Sir to says anything. I should be worried. Yes or no? Is there anywhere in your notebook?
Yes, sir. Noted it, sir.
Now you noted it. This type of collision is known as eccentric collision. It is not a central impact. Here, as you can see, this is the center of this. The impact is not taking place in such a way that the rod is going to rotate and not going to rotate. The center of mass of the rod does not lie in the path along that line of impact. The body is going to rotate. The body is going to rotate here. That is known as eccentric collisions. This is an eccentric collision. So the body is going to rotate now. Body is going to rotate. Do we understand this? Or is it about saying bye bye?
We understood, sir.
Well, you have to improve your memory, because we tend to forget things, and that's a very bad quality to have. Even I have a bad memory, but I don't forget what I've taught. That is one quality of mine that you will have to There is one quality that you will have to work around with, because I will not forget what I've told you. And when the exam comes and you bring your papers with me, and I'll tell you each and every question, and I'll tell you the lecture where I solved that question. I'll tell you the lecture. I've got everything that I've taught you from the very first class till now, till the last class that I teach. I will have all the records. And when your paper comes, I'll tell you with lecture number. This question was in lecture number this. Go and watch that lecture. This question was in lecture number this. Go and watch that lecture. Don't forget it. Otherwise, it's of no use that we're doing it. Anyways, moving ahead and solving questions now. As I've already told you that I've told you the entire theory part. The only thing that is left is for you to solve some question and feel happy about it. So now we'll just take the simplest possible case. And what is the simplest possible case here? This is a rod of let us say length L and mass M, and it is hinged about the highest point. And then this bullet of mass, I cannot call it M, so let me call it as M1, is moving with a velocity u. It strikes this rod and gets embedded into it. It gets embedded into it. Just sticks to it. Do you understand the meaning of embedded, sticking?
Yes, sir.
What type of collision is this now?
Elastic collision.
It's a perfectly inelastic collision. Okay, chalo. God is there, you know. Sometimes I feel that God has gone somewhere. Then you say all these things, and I start believing in God. Though my name says that one who believes in God is non-elastic, but I sometimes lose my faith. And it's because of you guys that my faith gets restored. So this is a perfectly inelastic collision. So kinetic energy is not conserved before and after the collision. So what will happen when it gets embedded? What will happen when it gets embedded?
Both will move together.
They will rotate. Okay. So first of all, you have to find out with what angular velocity will this rod rotate. That is question number one. Then this rotate will reach a maximum height. Yes or no? Huh?
Yes, sir.
You have to find out how high does it rise. Rise to certain height. Tell me how high that it rises. How high does it rise? So to tell me the value of this h. You have 2 minutes now to solve this question, get the answer, and stay happy. Let's see who gets me the answer first. Huh? Who will be the first one? Whatever. Take your time. Get me the correct answer. That is more important than anything in this universe right now. The universe, the entire universe is waiting for you to get the answer. The entire universe. Trust me on that. I've seen a lot of the universe. If you can do this question on your own, that means we have understood the concept of this angular momentum and all those things. Try. And once you try, trials never go unrewarded. You might not get the reward instantly, but you will get the reward eventually. Yes, anyone with anything that looks like an answer? Huh?
Sir, omega equals to m1 u by m plus m1 into L.
Huh? How did you get that answer? Tell me. Just like that, sir. I thought that this is the answer, sir. और अक्कड़ बक्कड़ बम्बे वो 80-90 पूरे 100. How did you get that answer, my dear friends?
Sir, I have applied perfectly inelastic collision.
Well done. Then what did you get from there? From perfectly inelastic collision, what did you get from there?
V equals to, so that is final velocity equals to m1 u by m plus m1.
What type of motion the rod and the rod is having?
Rotational motion, sir.
And what are you applying?
Sir?
And what are you applying?
Okay, linear.
The problem with you guys is you just forget what has been taught to you in just the last class, and this was taught to you in the last class. I don't know why you can't apply it. This was the thing that was taught to you in the last class. Why did I teach you all this? Just because I had extra time? No. Time is a luxury that we don't have, my dear friends. I can't waste a single second. Why did I teach you all this? Just for the that's you must know this. That's it. Yes or no? That was the reason I told you all this, right? Just knowing it. Let's know this. Nothing else. I expect that you can do this. That is what I'm expecting, but maybe my expectations are not correct. Obviously, someone teaches me quantum physics and gives me a question straight away of quantum physics, I may be not able to solve this, but the other person might expect me to solve it because he thinks that he has told you everything that is needed to know. That is what I think, that I have told you everything that you needed to know. Probably I was wrong. So now here I will apply what? I'll apply my latest tool, latest gadget. And what is the latest gadget that I have? What is the latest gadget that I have achieved? Huh? The name of this gadget is LOCAB, Law of Conservation of Angular Momentum. This is the latest thing that I have learned. Yes or no? No, yes. This is the latest in my artillery. This is the latest addition to my artillery is LOCAB. The linear momentum is not conserved, but the angular momentum is conserved. And about which point angular momentum is conserved?
Point oh, sir.
What exists? So I apply LOCAM about 0.0. What does LOCAM say? It says simply thing. Initial angular momentum should be equal to the final angular momentum. Then what happens next? Initial angular momentum. What is the initial angular momentum? Initial angular momentum is this angular momentum of this only one thing was there. This was this pink thing. This was the initial thing. What is the final thing? Now this pink thing is inside this rod, and this rod is my green thing. So this is my final thing, this green gentleman with the green bullet inside it. What is the initial angular momentum of this system? When I say system, what does this system comprise of? This system comprise of this pink ball and this green thing. What is the initial angular momentum of this pink ball? That must be equal to the final angular momentum of this green thing. What is the initial angular momentum? Say. What is the initial angular momentum? This is a particle. This. Bullet is a particle. So the initial angular momentum is, my dear friend, the pink one. What is the initial angular momentum of this pink one about this pink point? M into U into L. Yes or no? No or yes? So difficult. We have done so many difficult questions on this. We had done the question of the projectile. We had found out the angular momentum of the projectile about the center. This is very simple. MUL is the initial angular momentum. That must be equal to, my dear friends, what? The final angular momentum of this entire green thing with this green ball about this point O. This is in pure rotation. That must be equal to I, the angular, the moment of inertia of the entire system into omega. Now, what is the angular momentum of this entire system? The system consists of this rod and this particle, chota. What is the moment of inertia? About the point two, remember? This. 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 This 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 this. Oops, wrong color. this equation. I omega, I about that axis, I about the point of hinge. What is the momentum? Huh? What is the momentum? So on the left hand side, I have MUL. Sorry, not MUL. I must write it as M1 because the mass of the bullet is M1. M1 UL, that must be equal to moment of inertia. Moment of inertia of this rod about one end is ML square by 3 plus the moment of inertia of this particle about that point O, which is M1 into L square multiplied by omega. So your omega becomes M1 UL divided by L square, taken common, M by 3 plus M1. This is your omega, my dear friends, and I hope, oops, this is your omega, my dear friends, and I hope you have understood how I have achieved this. Yes or no? No or yes? Huh? Do we understand this, or this has gone above our saying bye bye selves? I have had enough of this. Yes? Law of conservation of angular momentum, my dear friends. Welcome to rotation. Do we understand this? Yes or no?
Yes, sir.
Pakka?
Pakka, sir.
Kacha pakka or bakka pakka? Or kacha kacha? So you have to apply law of conservation of angular momentum. But one question is still left. What is the height to which it rises? I always believe that students are like cash vouchers. Sometimes the cash voucher may not work. They will always get a chance to redeem themselves. So this is the chance of your redemption, my dear friends. Can you tell me how high that this rod rises? Huh? How high does this rod rises? Now, once this collision has happened, which was a perfectly inelastic one, after this collision, you can apply what? Because after this collision, the only force acting on it, which is doing anything, is gravitation. Our old friend gravitation. The force on the hinge is not doing anything, it is just on the hinge, not doing anything. Then you can apply your old friend. Who is your old friend? Here are two daughters working together. One daughter is Locam. What is the other daughter? Huh? What is the other daughter? The other daughter. You don't need mothers for this. Daughters can manage this one. The other daughter is known as LOCME, Law of Conservation of Mechanical Energy. You can apply this law of conservation of mechanical energy from this initial point A to this final point B, because now the only force working is gravitational force and it is a conservative force. You can apply the law of conservation of mechanical energy from point A to point O. So what is the what? For applying law of conservation of mechanical energy, I take the lowest point whose gravitational potential energy can be taken as 0. You understand this, yes or no? Right? So at the lowest point, what type of energy this system has?
Kinetic energy.
How much is that kinetic energy? Half into I into omega square. Yes or no, my dear friends? Yes or no? Half I omega square is the kinetic energy that this system has. At the highest point, the kinetic energy goes away because the rod is not going to go any further. It only has potential energy. So I've taken the potential energy of ground as 0. What is the potential energy this system acquires? Remember, the system consists of a rod, ding, 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 and a small bullet also inside it. So what is the potential energy? Ground ka, the lowest point of potential energy is taken as 0. So this bullet acquires how much potential energy? Is it a particle? Ding, ding. How much potential energy will it acquire? It has moved up.
MGH, sir.
M1GH. Do we understand it? M1 is the mass of the bullet. What about this rod? How much potential energy this rod has acquired? Huh? You have to see how much the center of the rod has moved. How much will the center of the rod move? The rod moves up by height h. Huh? Will it move h or something else?
H only, sir.
H only. H only. How much this point of the rod has moved? H only? Oh. How much this point of the rod has moved? H, yes. Upper part only moves nothing. So how much the center of the rod move? MGH by 2. Only moves half. Do you understand this, or this has gone above our head saying bye bye? Bye bye, sir. Bye bye. Bye bye. Bye bye or no bye bye?
We
You
understand.
understand this? Just to refresh your memories, this is the question that we did some 2 or 3 classes before. Do we remember this question? Huh? Do we remember this question? Yes or no? No or yes? Huh?
Yes, sir.
Here also the rod moves and the center of the rod also moves, but it moves only L by 2 sine theta. Do you remember this?
Yes, sir.
Thank God you remember it. So if you remember it, you must remember this thing. This is You must remember things, beta. Otherwise, whatever questions we are doing will not be of any use. Now, once you understand this, you can solve this question and you will get the answer because omega you have already calculated, yes or no?
Yes, sir.
And I also you have already calculated, yes or no? Yes or no?
Yes, sir.
And put the values, get the answer, and stay happy. Okay? Shall we move ahead?
Yes, sir.
Chalo, just to check, I'll give you one more simpler question so that you understand this. This one is the next question. A uniform rod of mass m and length L can rotate freely on a smooth horizontal plane. So my rod was hanging. My question was hanging rod. This is a rod which is kept on a horizontal plane. Can rotate freely a vertical axis about a hinge point x. A point mass having same mass m moving with an initial place speed u perpendicular to the rod strike the rod inelastically at its free end inelastically. Find the angular velocity of the rod just after the collision. You have 1 minute to give me the answer for this one. Do it fast as you can. Do we have anything that looks like an answer? I'm sure you have understood the question. Yes or no? No, yes, bacha.
Yes, sir.
I'm waiting patiently for your answers, beta. Can I expect an answer? Yes, bacha.
Sir, omega equals to 3u by L, sir.
3u by L. Let me check what answer I have. Definitely not the answer. Try. I would be very disappointed if you can't get this question. But I will have to come over that disappointment. The sooner I do it, the better it is for me. It is a very simple question. In fact, it is a exact copy of what I just did. Exact photocopy. It's a photocopy. I'll give you 1 more minute to show your talents, else I'll show mine. And I won't be very happy doing that. Yes, my dear friends. Any hope, or shall I give up and tell you the answer? Or shall I wait for a miracle to happen? Miracle that from somewhere the answer will drop. Or shall I stop believing miracles?
Do it, sir.
What have you tried? Tell me that. We find out what did you do. Yes, tell me. What did you do? How did you solve this question? What did you try? What is conserved here or what is not conserved?
Angular momentum is conserved about h, sir.
Angular momentum is conserved about the hinge, sir. That's it. You need to apply. What is the initial angular momentum, beta?
mu into L.
Locam, you have to apply about the hinge H. Initial angular momentum is equal to final angular momentum. What is the initial angular momentum? Initial angular momentum is the momentum of this gentleman. What is the momentum of the gentleman? Yes, MUL. This MUL must be equal to what?
I omega plus m into V.
So this gets embedded inside it because it is a perfectly inelastic collision. So this small particle of mass m also gets embedded. That must be equal to the green momentum.
It is just inelastic only.
What, beta?
Strikes the rod inelastically, no, sir.
So what do what do you mean by inelastic collision?
That is not perfectly inelastic, no, sir.
The book will not say whether it's perfectly. If it says inelastic, that is perfectly inelastic. Otherwise, they will give you the value of E. Value of E is not given anywhere. That means it is a perfectly inelastic collision. So you just got to do this. So your initial angular momentum is MUL. Moment of inertia of the rod is ML square by 3 plus moment of inertia of this particle is ML square multiplied by omega. Do we get this? Yes or no? From here, you will get the value of omega. And I think the value of omega that you will get will be 3u by 4l. And that is the answer, my dear friends, that I was looking for. As you can see, this question is an exact copy of the question that we had done. Do we understand this? Yes or no? No, yes. Remember, unless and until the value of E is given, you have to take it as perfectly inelastic collision, my dear friends. Do we understand this? Yes or no? No, yes. Huh? We understand it, bacha?
Yes, sir.
Chalo then, you will have one more chance to redeem yourself. And this is your redemption. Shawshank Redemption. Highest rated movie on IMDb. Redeem yourself. A uniform rod of mass m and length L can rotate freely on a smooth horizontal plane with a vertical axis hinged at the point H. A point mass having some mass coming with an initial speed u perpendicular to the rod strikes the rod and sticks to it at a distance of 3l by 4 from the hinge point. Find out the angular velocity of the rod just after the question. Your time starts now. And you have 2 minutes, and this is your chance for redemption. I hope you redeem yourself and move with pride that I have redeemed myself. If you don't redeem yourself, I would be pretty sad. This is a chance for redemption, my dear friends. Redemption, redemption, redemption. Can you redeem yourselves? Huh? Yes, my dear friends. I wait patiently for your answers. Yes, bacha. Bacha, I'm waiting. Shall I do the needful? Shall I solve it? You do it faster so that I can solve other questions as well. If you okay, take your time, take it.
Sir, it is 30
Yes.
cube by 43 L, sir.
Let me check the answer. 32 by 43. 36 by 43 is the answer, my dear friends. Not 32.
Sir, it is, I said 36 only.
36, yes. You see, students are like cash voucher. They can redeem themselves. So you have redeemed yourself. Well done. Again, what you need to do is apply what? Let me call this point as O. You can apply, you have to apply locam about which point? About the point O. Initial angular momentum is the angular momentum of this gentleman. What is the initial angular momentum of this gentleman? Huh? Pink one. M into U into 3L by 4. Yes or no?
Yes.
That must be equal to the final momentum of this gentleman, and this gentleman is inside this. The gentleman is inside this. So just do it. This is ML square by 3 for the rod plus M into 3L by 4. The distance is 3L by 4 square times omega, and we are done with the question. Yes or no? No or yes? Huh?
Yes.
Chalo. Anyone understand this? So then we move on to the next one, and the next problem is like this. I am creating it for you. Do it fatafat. The more the number of problems you do, the better you are going to become, bacha. This is a rod which is hinged at the point center. The length of the rod is L and the mass of the rod is capital M. Two particles strike and get embedded, one moving a mass small m, moving with a velocity u from here, the other one with a mass 2m, moving with the same velocity u, and they get embedded. Dang! So what will happen? Dang! Huh? So what will happen? This rod will what?
Rotate around point. Sir, that is
How will it rotate? Like this or like this? Clockwise or anti-clockwise?
anti-clockwise, sir.
So it will rotate anti-clockwise. You have to just find out the value of omega, and your good time starts now, because you are going to get the answer and you're going to stay happy. So your good time starts now, and you have exactly 2 minutes to get out of this problem. Your time starts now. Yes, bacha. Do we have anything that looks like an answer?
Sir, 6U by 19L, sir.
6u by 19l. I don't know the answer because I've created the question. So I will solve it alongside here. I will have to apply locam. About no problems. About the point O. I have got two ping balls here. And remember, the angular momentum of this ball is also like this. About this point, the angular momentum is also like this. So they are getting added up. Do we understand this? From the diagram, they are getting added up. Yes or no? Huh?
Sir, 1 minute, sir.
1 minute, sir. Garbar, sir. And then I have this green system. Ding, 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 ding. And in this green system, there are also two balls, mass M and mass 2m. So this green system will also move like this. Do we understand this? Ding, 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 ding.
Yes, sir.
That's it, my dear friends. So I apply the pink equation. And what is the pink equation? Pink equation comes from this one and this one. What is the pink?
Total 3MUL by 2, sir.
So for the first one, it is MUL. For the second one, they're also getting added up to MUL. That is the pink one. And then I have the green one. What is the green one?
L by 2, no, sir.
Oh, yes, 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 yes. Big mistake, big mistake. Sorry, sorry, big mistake. Genuine mistake. Okay. Then I come to the next one. Moment of inertia. What is the moment of inertia? Dung, 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 dung. So first is capital M L square by 12. Moment of inertia about the center of mass. Yes or no? Plus m small m into L square by 4 plus 2 small m into L square by 4 into omega. Remember that this was capital M. This was not small m. So 1L, 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 1L will get cancelled. I can also cancel this 2. So this will get 6. This will get 2. This will get 2. And you can end up, you can get your answer omega as, I think you will get 1, 2 getting cancelled. 3 M. Sorry, M will also get M will not get cancelled. 3 MU upon capital M by 6 plus 3 by 2 into small m multiplied by L. Do we understand this? Do we understand this? Yes or no? No, yes.
Yes, sir.
The mass of the rod was given different just for you to understand that it was different. Everyone got this? Chalo, I'll give you one more in this category to finish this category off. I hope everyone has noted this down. In this category, I will give you the mass as same so that that problem of cancelling m does not come. So this is the final problem in this category of eccentric collision. You have a rod of length L and mass of this rod is, let us say, 4m. I have just changed the scenario a bit. The block body of 2m, velocity u strikes like this. This one also mass m, speed u strikes like this. You have to find out the angular velocity of the rod just after collision. This is on a horizontal plane, and your time, the good time or the bad one, starts now. Good time if you can get the answer, bad if you don't get. You can always convert your bad into good. 2 minutes you shall have. Yes, bacha. Do we have an answer?
Sir, it is 6u by 13l, sir.
6u by 13l. I don't know the answer, so I will have to solve it. Let me call this point as O. I apply locam about O. Now, as soon as I apply locam about O, I must understand that there are two pink balls before the collision. Now, this pink ball is trying to rotate it like this, and this pink ball will try to rotate it like this. Who will win?
2m, sir.
2m will win because that angular momentum is more. Do we understand this?
Yes, sir.
So how will this rotate? It will rotate like this. Yes or no?
Yes, sir.
Anyone understands this? The angular velocity will be like this, clockwise, not anti-clockwise. So now I'll have to call the clockwise as positive, assuming that clockwise is positive. So what is the initial angular momentum? It is 2m into u into L by 2 minus m into u into L by 2. Do we understand this? Why I'm doing minus? Because they are subtracting each other. That must be equal to the final angular momentum. To get the final angular momentum, 4m
L square by 12.
L square by 12 plus, that does not get subtracted, remember, plus m L square by 4 plus 2m L square by 4. Do we understand this?
Yes, sir.
This entire thing multiplied by omega. Lot of things will get cancelled. Your m will get cancelled, your L will get cancelled, 1m, 1L, 1m, 1L, 1m, 1L, 1m, 1L, and you will end up with your answer. What is the answer that you are getting from here?
6u by 13l, sir.
6u by 13L. So I assume that this is the correct answer. You have done the calculations correctly. And that is how you solve problems of this nature. This was problems when there was a collision. Do we understand this? Yes or no?
Yes, sir.
Okay, then I'll give you one problem which has come in one of the JEEs. Let's see. Again, if you just understand the problem, you should be able to give the answer very quickly. So since because it is also related to some sort of impact collision, that is why I'm doing it here now. So this is the problem. Consider a body shown in the figure consisting of two identical balls, each of mass m, connected by a light rod. Remember, this system is not hinged. That is what I want to make out. The system is not hinged. If an impulse J is equal to mv is imparted to the ball at one of its ends, what would be the angular velocity of the system? The first thing you have to tell me is whether the system will move or will it only rotate?
It rotates.
Does it move? Does it move? It moves also. It did not move. two balls like this. You can consider a simple dumbbell, and you give this dumbbell a slap. It will only rotate, it will not move. It will also move. But here they are asking only about the angular velocity of that. Do we understand this?
Yes, sir.
Now the next question is, and that is the reason why this question was given, about which point will it rotate? That is the reason of giving you this question. There's no other reason. Huh?
1 minute, sir. 1 minute.
Should not take 1 minute. About which point will it rotate? About which point does it rotate?
Sir, it is 12/3 from M, sir. The point which is 12/3 from L. Sorry, 2L/3 from M. That is from left side.
Why?
Center of mass is at 2L/3, sir. After collision, center of mass is at 2L/3.
How did you get that? So you understand that it is going to rotate about the center of mass, yes or no?
Yes, sir.
The point is, how did you get the center of mass at 2L/3?
Sir, here impulse J equals to M/2 is imparted, no, sir. Means that is.
There is a 2 block here and I slap it. That means I've added mass to it. Huh? Is this a bullet coming and getting embedded that you consider it as a mass? When I slap something, do I put a part of my mass inside it? No. So the center of mass still remains at the center, my dear friend. This is not a bullet striking it. This is a slap given to it. Why will the center of mass change? Will the center of mass change? No. The center of mass remains at the center, my dear friends. You have to now find out the angular velocity of rotation of this. Any body which is free to rotate, it will always rotate about the center of mass, and you can do it. You have a dumbbell, you keep the dumbbell on a smooth surface and give it a slap, and you will see about which point it rotates. You will get hurt because you are getting a slap, but you will find out the physics behind it. So it will rotate about the center of mass, and the center of mass in this case is at the center, my dear friend. If this question would have been different, if a bullet would have been striking it and getting embedded, that was a different question. There is no bullet here, but this is an impact. Impulse given, boom! I hit it with a hammer, boom! What is the answer now, my dear friends? And I wait patiently for your answers. There's a lot of patience. Can I expect an answer, my dear friends?
Sir, option is A, sir. Sir, hello, sir.
Yes.
Option is A, sir. That is V by L.
Option is, I was
A.
looking at some other question. Yes, option is A, V by L. That is correct. What the answer? V by L. So what you got to do is you just need to apply your locam about this point. What is the initial angular momentum of the system? Remember, the system was at rest, but you gave it an impact. So because of this impact, this was an impulse given. This impulse provided it an impact. In fact, this is not a question of law of conservation of angular momentum, because angular momentum is not conserved. This is a question of impulse angular momentum theorem. The mother has to come now to save his daughters, because the daughter cannot do anything here. Why the daughter cannot do anything here? Because the angular momentum is not conserved. Do we understand this?
Yes, sir.
So you have to find out the impulse, angular momentum theorem basically. Now, if you just imagine that this hammer, whatever this hammer was, this hammer and this rod was one of your system, then probably you can apply law of conservation of angular momentum. But this is not a question of law of conservation of angular momentum. This is our mother theorem. Mother has to come. So mother comes now. Angular momentum or angular impulse, angular momentum theorem. Do we understand this?
Yes, sir.
Angular impulse, angular momentum theorem. So what is the angular impulse here? About the point O, because it is going to rotate about the point O. Yes or no? So my
Yes.
angular impulse is J, which is equal to, which is given as m into V, J multiplied by L by 2, and it looks like angular momentum only, right? Because the question was given in this way. If they would not have given J is equal to mv, then you would have been stuck. Oh, now what do you do? Do you understand this, what I'm saying?
Yes, sir.
Just because J was given as mv, it starts to look like law of conservation of angular momentum, but it is not. J is the impact. So I'll solve this question in terms of J. Then I will write the value of J. So it is J into L by 2. That will be equal to the momentum. What is the moment of inertia? M into L square by 4 for one. For the second body also same. So 2 into M L square by 4. Yes or no?
Yes, sir.
Into omega. So from here I will get omega as, because this question could have come in a different way. Instead of giving it as J as MV, they could have just given it as J. So remember that. So I'm just solving it as J. So omega will become how much? Ding, 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 ding. So your omega will become J by ML. Do we understand this? So that is the answer for this question. When you put the value of J as M into V, you will get it as V by L. But that is the better way of understanding or doing this question. Do we understand it? Or is it gone about? I think bye bye, bye bye, sir, bye bye. I don't understand the mother. I only understand the daughter. The mother theorem will only come when the daughter theorem cannot help you out. And here, the daughter theorem cannot do anything about it. Shall we move ahead?
Yes, sir.
Okay. Okay. Now we have done with the questions on collision as such, which were the more difficult part. Now we'll come across questions which may not look like questions of collision because there is no sudden impact, but things are going to come in contact, or things are going to, the moment of inertia is going to change, or something is going to happen. So remember, if you have a system of rigid bodies, so you can write some important points here to solve questions like this. Point number one, the type of question that we are going to do now may not look like collisions. They are collisions in one sense. Now, if you have this, sometimes you are going to have this, you are going to have a system of particles where the system would be rotating with some angular velocity, and suddenly the moment of inertia would change, and then you will have to find out the final angular velocity, of the body. The best example that you can give is mm, this beautiful lady doing ice skating or gymnastic. Now, you may have seen that they when they're performing their skills, they start to rotate on their one axis, right? And suddenly they spread their arms, and then they get their arms together. When they get their arms together, their speed of rotation becomes more. Do we understand this?
Yes, sir.
Why it becomes more? When they do it here, their speed becomes less. When they do like this, their speed becomes more. Why? Eh? Because of law of conservation of angular momentum. When they spread their arms like this, their mass gets away from their axis of rotation. So their moment of inertia increases. When they do it like this, their moment of inertia decreases. So you can find out by the law of conservation of angular momentum. You can find it out from the law of conservation of angular momentum. What will be the final angular velocity? Yes or no? No or yes?
Yes, sir.
Eh? Similarly, this gentleman, turntable, this gentleman is doing some bicep exercise, and when he does his biceps like this, and the turntable rotates, and when he does it like this, the turntable will start to rotate faster. I1 omega 1 is equal to I2 omega 2. Same thing. The lady can do the gymnastic one. This gentleman cannot do gymnastic, but he can do this exercise. So he's doing this exercise. Do we understand this? Huh? Examples where you can apply this. Do we understand this, or this is going above and saying bye bye, sir? These are internal forces. He is using his muscle power. He or she is using his muscle power, which is an internal force. Do we understand this?
Yes, sir.
Similar to this is a question here where you have one disc rotating, and you put another disc on the top of it, and then this disc will come to the same angular velocity. Whatever is happening between these two discs is because of the friction between the two discs. That is an internal force, so the angular momentum will remain conserved. Do we understand this?
Yes, sir.
I hope you are noting it down. You may not be able to draw the diagram, but you can definitely note them down. Yes or no? No or yes?
Yes, sir.
Now, again, we are just after this chapter. The next chapter that we are going to do is gravitation, and in gravitation, we are going to see the motion of what? The motion of planet around the sun. Here also, the only force acting on them would be the gravitational force, and their angular momentum about the center of the sun will remain constant. So when the planet is far away, the angular momentum is more, so the angular velocity will be less. When the planet comes near, angular momentum becomes more with respect to the center of the sun, and the omega increases. Do we understand this? Yes or no? No, yes.
Yes, sir.
Then there is one more thing that I've seen questions on this coming. What happens if the what, the radius of the earth changes? What effect will it have on the time period of earth? I've seen this question, so you can note this down as well. This one, my dear friend. So when the radius of the earth changes, the what, moment of inertia changes, and you have then this. You understand this, or it is gone above it saying bye bye? Bye bye, sir. We are done. Hello, do you understand this?
Yes, sir.
So now I hope you have noted down all these different cases. Yes or no? No or yes? Have you noted it down, beta?
1 minute.
I'll give you 1 minute. Don't worry. I was thinking that I could finish angular momentum today, but it seems like I could not do it. Not a problem. I will extend it in the next class. Not a worry. I can't pull the curtains down unless I feel that we have covered all questions that can possibly or potentially come in your exam. So even if it takes one extra class, an hour or a half hour more, I would dedicate it because I don't want to leave any stone unturned. Because at the end of the day, if a question comes that I have not discussed in the class, I would feel ashamed of myself. Why did I not discuss it? Not because I could not have discussed it, just because probably skipped my mind that I could not discuss it. There is no question that is going to come in the exam which you cannot do or which we have not discussed, and that is the entire purpose of this class, to cover each and everything that can come in your exam. Let me know once you are done, bacha.
Sir, it's done, sir.
It's done, sir. Then I will leave you with this problem for you to solve. And we will be solving problems of this nature now, where you don't see to have a direct impact, but all these are also questions of collision. The only thing is there is no direct impact. You don't see a very good big impact force, but you will see whenever two bodies are interacting, it's a collision. Here also the body is interacting. One disc was rotating, dung, 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 and then you put four masses on this. This question, once you do this question, which I will ask you to answer tomorrow, the other version of this question is a disc is rotating, two small masses are here, then they start to move outward. When they reach the outer ends, what is the angular velocity of the rod? So these all questions are similar in the sense that only one thing is happening here. Because of the internal forces, the moment of inertia of the system is changing. Do we understand this? Yes or no? Because of change in moment of inertia, basically the angular velocity is changing. So we will be discussing these questions in the next class, and then probably move on to the last part of rotation, which is plane motion. The body is going to rotate and also move. So that becomes the most difficult part, which we shall tackle from the next class onwards. Today is Friday. I can't finish it by Saturday. So probably by Monday, we'll be able to finish your rotation. Okay. On that note, please work on the problems. Are you done with your exercise that I sent you? How many of it is left? How much of it is left? Huh? Sir, I don't know the exercise. What exercise? I don't get time to solve it. Yes, how much of it is left?
Sir.
Array, I sent you an exercise, that sheet. What
Okay.
going with that?
It is almost Completing, sir.
Good. Well done. Then I'll see you in the next class tomorrow, and I'll try to wind up angular momentum and start with your plane motion. Take care. God bless all of you. Bye-bye. Please work on the problems. Your rotation is not going to get any more better than once you finish rotation. Remember, when you are doing a topic, you are the best at that topic. 3 months after that, your level is going to go down. So you can do the best problems now. Do them and remember them. Take care. Bye-bye.
Yes, sir.